G'day everyone, and welcome to our lesson on transformers practice questions. Here's how a transformer basically works. You've got your primary coil here and your secondary coil here wrapped around an iron core. You change the current through the primary coil. This generates a magnetic field through that primary coil, as well as a magnetic field through the other coil over here. So primary coil, the current generates the magnetic field. The secondary coil experiences that magnetic field and it flows through those loops there, so behind the green lines that we're seeing. This sudden appearance or change of a magnetic field over here in the secondary coil actually changes the flux, and flux is given by the strength of the magnetic field multiplied by the area in those loops, and then the change of flux in here results in an EMF given by Faraday's law. So the voltage, the EMF, is given by N, the number of loops, multiplied by the change in flux over the change in time. Now this part of the formula tells you the EMF generated in one loop, or generated by the change in flux in a single loop, and if you string a bunch of those loops together in a coil like this, you can really bump up the voltage. So the first question asks us to design our own transformer. And the requirement is that if you have a source, a voltage source, excuse me, over here of 200 volts, and you want to get it down to 10 volts over here, they want you to design a transformer that will achieve this. Well, let's use this formula over here. The ratio of the secondary voltage, Vs, is equal to 10 to the primary voltage, Vp, is equal to 200. Is 10 over 200, which is 1/20th. And that has to be the ratio of the secondary loops to the primary loops. So there has to be one secondary loop for every 20 primary loops here. So let's say we have 400 NP, 400 primary loops over here. We said that there has to be one secondary loop for every 20 primary loops. So if we divide 400 by 20, we should get the number of secondary loops. And that comes to 20 secondary loops over here. NS is equal to 20. So it's not really about the number of loops we're using, it's more about the ratio. So we take these two numbers together, and we could equally well have made this 800 loops over here, and if we've doubled the number of loops on the primary, we double the number of loops on the secondary, and this would work equally well. Remember, when the voltage on the primary is greater than the voltage on the secondary, the voltage is going down across here, which indicates it's a step down transformer. The next question is a little more difficult because it brings into play concepts to do with electric circuits. And it's basically going to prove the transformer can only step down the voltage that's available to it. So say I have some kind of AC power source over here. Remember, transformers can only work with AC because it's only with AC that the direction and magnitude of the current is changing. There is a concession, you can make a transformer work with DC as long as you're constantly changing the magnitude of the DC voltage. But ignoring that for now, we have an AC voltage source, magnitude 20 volts, being transmitted over wires which feed into a transformer over here. And on the other end of that transformer we have loops which leads to a globe over here. And that globe has a voltage associated with it and an amperage. Okay, the resistance in the wires is 2 ohms going that way and 2 ohms going this way. And when we measure the current, we find the current in the wires over here was 1 amp. Let's figure out the voltage and the current in this circuit over here. So we start off with 20 volts and we're going at 1 amp. So the power being generated to the entire system over here is equal to the power generated here. And that's equal to VI, which is 20 times 1, 20 watts. Let's find out how many volts are lost over here. The volts lost on this wire heading to the transformer is equal to IR, Ohm's law, which is equal to 2 times 1, 2 volts. And likewise, there's 2 volts lost here. So if we lose 2 volts here and 2 volts here, the transformer only has 20, take 2, 16 volts available to it, and that is what it steps down. I forgot to mention this. The transformer has a ratio of 4 loops on the primary to 1 loops on the secondary. This is a step down transformer. There are fewer loops on the secondary than on the primary. So this 16 volts here becomes 4 volts over here. So the voltage available to this globe is 4. Furthermore, the current running through this coil here was 1 amp. So the voltage was 16 and the current was 1 amp. The power on this side of the transformer has to equal the power on this side of the transformer. P equals VI equals 16 watts. So there has to be 16 watts over here. P equals VI. 16 watts is equal to 4 volts times some current. 16 on 4 is equal to 4 amps. Notice that the voltage has been stepped down by a factor of 4, from 16 to 4, and the current has in turn been stepped up by a factor of 4. Let's figure out now the power loss associated with the wires here. Using our common sense, if we had 20 watts available over here and only 16 watts have been used on the globe, we're expecting a total of 4 watts to be lost, 2 here and 2 here, because of the symmetry of the 2 wires. So the power loss here is given by I squared R, which is 1 squared times 2, that's 1 times 2, 2 watts over here, and then 2 watts down there. So everything fits together very nicely. The last question I'm going to look at involves Lenz's law, and that tells you the direction of the induced EMF. This will take some drawing. Say I have this bar, and it is a solid bar, and then I have a battery down here with a switch which is currently open, and that battery runs up and loops around like so, and then I have another circuit on this side with points A here, B here, and some kind of resistor in the middle. So I'm going to vocalize Lenz's law here. It's a bit long to write. When a loop experiences a change in flux, we know that a voltage is generated. The direction of the current caused by that voltage, so the direction of the induced current, will oppose the change in flux. And we'll see how that works in a second. If I slam this switch down and open up this circuit to charge, the charge will flow out of the positive side of the battery and around this coil here. Let's figure out the direction, either A to B or B to A, of the current in this circuit over here. So that's the goal, the direction. So I close that switch there. The current begins flowing in that direction. Using our right-hand grip rule, where you put your thumb in the direction of the current and you curl your fingers around, your fingers should point that way there. That is the direction of the magnetic field lines created by this coil over here, and they reach this coil over here as well. So there was zero flux, and now there is flux or magnetic field in this direction. The current in this coil will flow to oppose that change in flux. So flux is increasing this way here. The current will flow in this coil to push magnetic field lines in this direction. So if we were to wrap our fingers around the wire so that our fingers are pointing in this direction there, behind that wire, our thumb would be in that direction. Try it. Put your right hand on that imaginary wire and curl your fingers around it. Your fingers will be pushing in this direction here. If the current were to flow this way, we'd actually be helping the flux increase in that direction. So the current is flowing down around here. Keep drawing. So from B to A.